G'day all, this is Tim. Today we're going to be looking at how to design FPGA projects. When I look at a design, the first thing I need to do is have a plan. So FPGA, although when we do it, it looks a lot like we're coding. If you think of it as an electronic circuit where you've got a whole bucket of components, you wouldn't just sit down and randomly throw them in. You sort of have to plan out what you want each part to do, and that's exactly what we're going to be doing here. So the steps that we'll cover to do this is defining the scope, knowing what it is that you want your circuit to do. Once we know that, we can break it down to the simple parts. So each part can be considered like a discrete electronic component, such as an AND gate, a counter, an output, an input, a switch, those sorts of things. And once we've got all of those discrete parts, we'll combine related parts back into a block. So what we're going to walk through is how to create a LED or matrix array. While one of my individual parts will be an LED, we'll create a block to make up 64 of them in an 8x8 matrix. And within that block, we'll then define what input outputs we need. So we're going to need a clock, some serial data, obviously power, and possibly resets and things like that. We'll repeat this for each of our blocks, so we might need one for some memory, some user input. Yeah, so we'll work that out as we go through. So we interconnect each of those blocks that we've defined, and once we've interconnected them all, and this is just on paper at the moment or in some sort of a basic drawing program, we can check for the areas that could be improved. So you might find that there's something that's duplicated or a signal that you've outputted that you're not really needing. So we can chop things out before we've even started doing any real work. And at that point, we'll look at how to start coding the most important block. Now, most of this will come into the following video, but we'll just go through with a flow diagram of how to approach that sort of thing. All right, let's get started. Okay, so step one, we're going to define a scope. So our scope is all of the things that we want this to do. So we want to have a matrix display. In my case, I'm going to be using these boards, which have a series of programmable LEDs, sometimes generically called neopixels. These ones are a WS2812B, and I want to build them up into an array. So it can be a 4x4 array like this. So we've got 16 by 16 LEDs or pixels consisting of 8 by 8 arrays. So we want to have 4 times by 8 by 8 array, LED array. Let's take them out of the way. We want to display on that array the numbers 10 down to 0 as a countdown. As the countdown's getting closer to 0, we might change the color. So change colors. We'll need to drive this, we'll need some sort of data in. So we're going to need data, which will be the numbers. Now that may be from an external source or an internal source, we don't know yet. We're just sort of defining a broad scope. We may need something to reset it. So if it is halfway through a count and we want to reset it, we might need a push button or an input to do that. We're obviously going to need some power sources. And for the LEDs, these need plus 5 volts. But for the MPU, or the FPGA I should say, we need a 3.3 volt rail. So we're going to need a couple of power sources there, which, given that the data coming out of my FPGA, the pins, the I/O pins are going to be 3.3, we're going to need a level converter. The current on the power supply, we don't know yet. We need to calculate how many LEDs will be on at any given time and multiply that current. We'll say current So the number of LEDs on, which will be times by, we'll say 20 milliamps, which will be varied on the intensity. Okay, I think that's probably all we need as the basic scope, and from there we can start to break it down a little bit further. So things like how the data is going to go in there. So that might be a ROM, and it could be that we hit the reset and it automatically starts counting, or it could be computer, so PC. There's various options there. So what we'll do now is we'll start to look at the building blocks. So we said that we want to get right down to component level. So this is a module which has 64 components on it. So what I will do is we're going to start off and say that we have a single WS2812B. So that is a LED that has 5 volts, 0 volts, and data. And it also has an output. So it's got data in and data out. So you basically stream data into it, it reacts to that data string, and it continues to send that on to the next device in the line. Now we need to understand what it is that's going to happen to make this actually light up, and to do that we need to go over to a data sheet. And here we are at Weld Semi, who manufacture this particular item. Be very careful to make sure you get the one with the B, which I'll show you in a moment, the mistake I made by just going for the WS2812, not B. Wasted a lot of hours. So in the data sheet, we've got various things about this that tell us that we can get up to 30 frames a second if we're using 1024 of the individual pixels, so one LED is 1 pixel. So we can effectively give TV on here. The data that we send to it is at 8 kilobits per second. So we'll write that down on my sheet. So that one is 800 kbps. Be upside down. All the joys of being dyslexic. And scrolling further down, we get the footprint. But what I'm interested in is timing data. So we can see here that they're saying 12 milliamps under various tests they've done of brightness and color wavelength. So I'm going to work with 20 milliamps, which is a fairly safe number. But what I'm interested in is these timing values and transitions. When we send data into one of these devices, we send it into the first LED, and then internally it will send it to the second LED, third LED, and so on. But because it's just a serial data, we don't actually just send 101010 because we have a long string of data to send through. So what we do is we send a 24-bit data word which tells the first LED what to do. And it starts off by sending the green color and intensity. So we've got 8 bits for green. We've then got 8 bits for red and 8 bits for blue, which makes up our 24 bits. And what that will do is come into this data in, and the first LED will pick up what it needs from it, and then it will be passed on to the data for the LED 2, which brings us back up to this table. So what we'll see is the first LED will take its 24 bits and only pass on the remaining string. So let's say we've got 64 LEDs to play with. We would have 64 of these 24-bit data packets. First LED would light up based on what we've sent it and strip off its data. Second LED will do the same and strip off its data. Third LED, and so on. Then once we've got to 64, we need to send a reset period, which is a low pulse for greater than 280 microseconds, and then we can repeat it if we want to change the display. If we don't want to change the display, we don't need to actually send anything. It's only if we want to update it. So I'm just going to make a note that we need, so green from 7 down to 0, followed by red 7 down to 0, followed by blue 7 down to 0, and that's our 24-bit word. And our reset signal will be greater than 280 microseconds, and that will basically say that we've got to the last LED in the array and we want to come back and start working on the first LED again. Next we're going to look at the timing that we need to do for each bit. So when we were talking about the sending of, we'll say, the green bits or the whole word, let's say we're just looking at that single bit there. To send that, we need to send for a low a certain pulse width high followed by a certain pulse width low, and for a 1 it's a different pulse width high and low, and for a reset it's just a low. So the timing of those values, if we wanted to send a 0, we would need to send a timing pulse somewhere between those two values, 220 nanoseconds up to 380 nanoseconds. So I might just say 300 for my purpose. So that will be as a high pulse, this part here. And then for the 0 low part, we're going to send anywhere between 580 nanoseconds up to 1 second. So we might just say that's a 600 nanosecond pulse, which we're sending is this portion here. So that would represent a digital 0. If it was a digital 1, we start off by sending the high pulse. Again, we'll say 600 within that range. So that is this length here. And then for the low pulse for the digital 1, we also need to send within that same value. So it can be 600 milliseconds again. So timing. So for a 0, we need to go like this. So we said that we'll make this part's 300 nanoseconds, and this part was 600 nanoseconds. And then for a digital 1, we had 600 nanoseconds and 600 nanoseconds. And for a reset, which we've already got up here, we just need to have a low, so I'll just draw it as a low going pulse, and that has to be greater than 280 microseconds, so a huge amount longer. And that will return from LED 64 back down to the first LED. So we have our timing, we know our data structure, and our data rate. Other things we're going to need, because in an FPGA typically everything is synchronized with a common clock, so we're going to need a clock, and that clock will be used to drive that 800 kilobits. We'll need a method to process each of these bits, so we're going to have a 24-bit word, but we need to send that to the LEDs 1 bit at a time. So we need a method that will take each bit one at a time and send the high pulse and the low pulse, and then come back and get the next bit, repeat high pulse, low pulse, and do that for all 24 bits, keeping a track of which one it's up to, and then move on to the next LED. So after 24 bits, repeat for next LED. Okay, I think that is probably enough for us to get started. We've got 4 major parts just to drive one LED, and then it'll be a case of repeating that same cycle for 64 LEDs, and then we can build that up to the 4 rows of 64. Now, while we're talking about timing, I just want to point out that when I started this project, before I started doing this video, and was doing some experimenting, I actually looked up on Adafruit's website, their NeoPixel, which I didn't really realize that it was missing the B on the end of the part number. And I worked on all of these timings, and they don't work. And I also got the same timing from a few other sources. But yeah, just be aware that the NeoPixel from Adafruit does not have the same timing. All right, so I'm going to jump off and do a little bit of a flow chart, and then I'll come back and explain that. So this is the rough flow diagram that I've come up with for this part of the project. So I've drawn it for a 64 LED unit, but we'll look at it at steps of just the initial 1 LED. This part here is where we get our 24-bit word, and that comes from something external. I could use some carrier detects and things, send readies and all those. Not sure if I'm going to need it yet. And we will store that internally inside of the unit. So the part that we're looking at basically incorporate these bits here at the moment. So this is just the building block to drive the row of LEDs. In fact, probably even chop that bit out there if we wanted to. So what will happen is we will get our word in, and this function here will send it as individual bits. So we've got 24 bits came in, and we're going to send them out as individual bits. So down here we will receive a bit, and we'll define our timing based on the timing values we looked up before. And depending on whether it's a high bit or a low bit, we'll choose how to set up our two timers that we're going to use. So if it was a high bit, or a low bit for that matter, but we'll follow the high bit, we'll come down this path and we'll set our output to a high. So let me just draw that we've gone from a low, we've gone to a high, and we're in a timer here. Now all of this timer is being driven by the main clock, which I haven't drawn into this. And we will keep on counting down until the value we set up here reaches 0, at which point we'll need to drop into another function, which we're going to use as a state machine. So that will drop down. This will again do a timing loop until we get to 0. And the data bit, if we're just done the first bit, which was 23, so we've started at bit 23 up here, we will have now gone to bit 22. So we go up here, we get the next bit. So if it was a 0, we set up our timing for a 0. We come in, and again we will do our timing. Again, it'll have the same overall width of 1250 nanoseconds, but from there to there will be 1250 nanoseconds. And if we go a little bit further over, from there to there will also be 1250 nanoseconds, but the timing of the high portion will be different for a low bit versus a high bit. So we're basically going to keep on looping through this for all 23 bits in the word, and that will set the color and intensity of the first LED in our array. If we've got to the bit 0, so we've finished one full LED, we're going to have to change the LED position. So we've gone from LED 1 to LED 2, so that will take us up this path where we will get a new complete word and store it, and start at bit 23 and repeat. And then when we've done this 63 times, on the 63rd time we're at the last LED, we basically need to send our reset delay. That's the 280 microseconds. That will tell us that we've gone all the way through the whole row, and we start back at LED 0, or the first LED. So this is basically how I would intend to work on my coding for that particular part of the project. Alright, so we've come back, we're looking at the bits that we needed to do, so we've sort of worked out roughly what we need for the LED array. How are we going to do the numbers? So let's grab a new piece of paper. So for this one, I think that I will use some sort of a ROM. And that ROM, because we're working on the 4 by 4 lots of these, we'll need a 16 by 16 arrangement to store the data. So we just basically need to create an array for that. Do we need to clock it out? Probably not. So our ROM can be as simple as that. There's no need for clocks or anything. So it's got two things. We've got an address in, and we have data out. So the address system, we haven't defined anything yet, but we've got 10 characters, so it could be as simple as 0 through to 9 as our addresses. And the data out will go to the input to the LED array that we've just been talking about. Okay, so we need a method of counting down, so we're going to need a counter. So from 10 down to 0. So that's just a decade counter effectively. If we talk traditional digital electronics, that does need a clock pulse. It will need a reset. So they're both inputs, and the output from that can actually be used as our address up here. So this one would have to give us a 4-bit output /4. So that shows me that I've got 4 wires, which will go up to here, which is also a /4, and my data will be a /24 for 24 bits of data. Alright, I'll just change colors. So my clock, depending on how we want this count to work, we haven't said whether we want it in seconds, minutes, whatever, but we will need to scale. So we'll need a clock scaler, and let's say it's 1 per second. So that will be getting pulses once a second and giving us an address out. So somehow we need to create a scaler there. Okay, so I think we have covered that one off. Now we want to change colors. So we might start off as 10 down to 5 is green, 5 to 3 is blue, and 2 to 0 is red. So we're going to need to keep track of where we are. So somehow off of this counter we will need to also track. So just displaying it is not necessarily the right solution. It might be that we want to come through the track count and then output it. In fact, I'm pretty sure we will because of the colors. So that gets the ROM, we track the count, so that's going in that direction, and that's a /4. Okay, so we then need to do some ifs. Let's make this box a bit bigger. So we say if it's greater than 5, it will be blue. It looks like a 75, but it is a greater than 5. If it is less than 5 but greater than 2, it's going to be blue, and if it is less than 3, it'll be red. So we need to build some logic around that, and that will output the color code for those portions. Okay, then our data, we're going to need some method of displaying that. Looking back at my notes here, so I've actually, my data ROM was what I did. The countdown we've done, so it's the changing colors. So we will need the data to come into a function, and also the output from this. Now I've said that's 24 bits. Because it's just the character, it will not be 24 bits. I'll change that in a moment, we'll come back to it. This will be the 24, which is the color data. Okay, so this is color mix. So that will put the color on the appropriate data. Will that need a clock? It needs to know, it gets that data and that data, not necessarily, but it's probably a safer way of doing it if we include a clock. So I think all of my modules should have a clock, and that can be this same clock source here, because that will all happen at the same time. I may change that later, but that's my thinking at the moment. So I've mixed our color. Our ROM has given us a huge piece of data. We only want it one row at a time technically, so we've got, so to drive pixel number 1, we're then going to scan through this row, then over through this row, then over through this row. So we need to plan the data that we get so that this is only one, is it 1 bit? Yeah, so it's just 1 bit at a time. So the way this has to output, we're actually going to need to change that addressing a bit. So this is the beauty of going through and thinking it all out at this level, is I'm starting to see the holes in my system. So my simple counter 0 to 10 would be fine if I'm outputting the entire digit, but I don't want to, so I need to break that up, that I'm actually, for each of my digits, outputting whatever 16 by 16 multiplies out to. I need to do them one memory location at a time and put that through. So I'm going to do some. So I stopped at this point and had a bit of a think about how I'm going to arrange my ROM and how I'm going to get my data to my matrix display. So my matrix will basically be the 4 of these. So 1, 2, 3, 4. And what I'm thinking I will do is just send 1 pixel at a time from my color mixer. So over here, my ROM needs to be 10 lots of 256 bits to give me my 16 by 16. So that data is going to come into my color mixer, and all I'm going to do is take the very first pixel, so whether it be a high or a low, I'm going to mix the color data onto it, and I'll send that out here as a 24-bit data bus. So I'm only dealing with 24 bits wides of data. I've got to clock that at 50 nanoseconds, which is how we get our 800 kilobits per second drive to this. And what I'll do is, internally in the logic for this, I will update LED 1, and then LED 2, LED 3, LED 4, and then it will go down each row in lots of 8 until we get to 64 down here, and then we'll repeat for number 2, 3, 4. And because the refresh rate is so fast, we're not going to see any flicker or anything on that. So that's my plan, and this is the beauty of sitting down and drawing it out beforehand. So I've gone down to my lowest level where we just looked at the individual pixels. We've then built that up into how we need to do timing and all the core details of that. And I've been able to go from there into these different modules that I need to build. So for each of these modules, I'll need to go through and do a bit of a flow diagram. May need to refine this a little bit more, but this is my thinking on how I'm going to get to my end result. Whereas if I just sat down and started doing the coding in the FPGA, it would be a big mess. It would literally be like throwing a bucket of chips on the floor and, you know, randomly plugging them in and seeing what result I got. So I look forward to seeing you in the next video. Make sure that you click the like, subscribe, and it's going to be fun. See you then.